Right, so I want to talk about synthesis and verification problems in the context of communication networks. Maybe if you were at this class year, you may know 2-3 slides from it, but hopefully not much more, okay? Networks are, just worked a second ago.
Unreliable.
Yes, exactly, I did it on purpose. Networks are a critical infrastructure, so basically if they break, they can have knockout effects, knock-on effects, okay? There's this story from Facebook, so in 21 they had an outage in their network, but actually that took down their social networking site, but actually it also took down Instagram, WhatsApp and other related applications they had. And there's also this story that actually also their internal systems got disrupted. So basically some of the engineers, they had to break into their own buildings to go to work because the whole system kind of went down. Okay, so actually, of course, there are many other examples like that. And actually, even, for example, 9/11 network was one that had an outage, and of course it's really bad if 9/11 network or 112 network is out, because that's really for important things. And what we can see is that a lot of the outages are actually because of human misconfigurations. So communication networks are really nice for formal methods, because currently they're really manually driven and operated and maintained, but there is a lot of potential to automate things and hopefully what we call make them self-driving, so they're really fixing themselves and repairing themselves. I want to show you one example why this is not easy. So this is a case in a Microsoft data center, and they had basically configured the network very well. So they had some global services, so they run applications or services that should be reachable on the left side of the data center. And then they also had some services that should stay inside the data center on the right. And they did everything correctly, so they configured the routers at the border so that they'd say, okay, if traffic comes from the publicly available services, then let it through. And if it comes from the private side, then please block it. So, I don't know, anyone has an idea what went wrong in that Microsoft data center? It looks, everything seems relatively easy and clear and well configured. It's maybe a bit hard to see, but what happened is that, what can go wrong here, that there was a link failure. And basically, when a link goes down in a network, then traffic is rerouted on a different route, okay? And now what happened here is that the traffic from G to Y, or basically the traffic from G to X, which should go to X, then was rerouted via Y, and then went through this global side of the data center, and then from there, it was led through because to X it appeared like this is coming from the globally reachable services. So if you already see it's complex to configure a network for a human, then it becomes even much more complex if you also need to think about failures. So to check whether a configuration is policy compliant even under failures is something that is quite hard to achieve for humans. And many networks, they have this feature, that's why I want to present it here, because it's about locality, that routers reroute traffic locally. So if a link is down, they reroute it in a different link. And basically, there is like a slow way to react to failures in the control plane, where you recompute each other's paths. But then there is also a fast way, that is a local way to react to failures, that is like the so-called data plane, where a router just goes on a different link if another link is down. So the kind of decisions that we have to make in the router is the following. So this is just the reaction of a single router. And basically we have in the router these match action tables. And when a packet comes in, you make a match and then you decide where to forward the packet. So what can be taken into account there is, for example, the packet header. So, but also the port where a packet arrives from. So in order to decide where the packet should go, I can look at the header and I can also look at the ports. And I also know which links have failed incident to myself. So this is the kind of information I have locally at the router. And then I need to decide where do I forward such an incoming packet. Okay, so basically link failures happen, so networks become larger and larger. And actually copper links that we had in the past, or copper cables that's still around a lot, they fail also, and the more you have of them, the more they fail. But now we are moving more and more to optical links, and they fail even more. And then NVIDIA, for example, these NV links, there has been studies like in the GPUs, they have even higher failure rates. And they're not just failing, but then they're coming back and then failing again. So it's something we cannot rely that the link is there. So we need to basically do something about it. And there are two aspects to it. One is verification. So can we check whether the configurations and entries in the router are actually policy compliant even if there is a link failure? And then you want to do the synthesis is kind of, can we generate routing configurations so they have a certain failure tolerance? And this is especially hard if you have like multiple failures at the same time. And there are two notions of resilience considered in the literature that have very confusing names. One is called ideal resilience, which means like I have a k-connected graph, and can I always find the path if there are up to k-1 link failures? That's called the ideal resilience. And there is perfect resilience, which means that can I always find the path if after the link failures we are still connected, so that the graph is still connected? Or in the subcomponent where we are still connected, can we still find a route? So is it clear what's the difference, or which one is more powerful, or which notion is more desirable? Either, how do they relate? Is it clear?
I mean, it sounds like perfect resilience, if you can achieve it, is better, because the other one is about k failing, but you use this like number k, but you don't talk about which k, you kind of universally quantify, and then it's a bit weaker, but...
Right. Very nice. So perfect resilience implies ideal resilience. It's stronger, because in ideal resilience, by definition, the graph is still connected. So we only have k-1 link failures, and then we need to find a route there. And actually, it's a big open conjecture. Can we always achieve ideal resilience? Of course, if we do it in a global view, I can compute shortest paths and I will always find the path. But now we need to make these local rules that we saw, that we put on the routers, and just say, okay, if the packet comes from here and it has this destination and this link is down, what do I do with it? So it's a big open problem, algorithmic problem, kind of a graph theoretical problem that some subgraphs, special graphs have been understood, but in general, we don't even know is it likely or unlikely that this is the case. Yes?
When we are putting these rules into the router, do we assume we know the normal graph structure?
Yes, exactly. So you know all the graph without the failures, basically. Exactly. So you need to pre-install them without knowing the failures. And then here the assumption is they fail all at the same time. So, okay, so yes, so here this is the conjecture I mentioned. Just to let you know why this is not trivial. So let's say you have a connect, you want to route from S to T, and if the graph is k-connected, it means that you have k disjoint paths, right? So there may be multiple nodes along these paths. And in principle, you could just try to basically try one path after the other. But in order to do this, you need to be able to match the source, you need to be able to match the destination, and you need to be able to match the import. Because then you can kind of pre-compute all these parallel paths, and then you go for the first one. If you fail, you send the packet back. And just to send it back, you already need to be able to match the import. Because if you don't remember did the packet come from left or the right, then you already may be in a loop. And then you send it back to the source, and then the source sees, this was my packet, so now I will try the next disjoint path. So if you can match the source, the destination, and the import, you can find it. But the conjecture is basically related to what if I can only match the import and the destination, but I cannot match the source. Because this no longer works, going back to the source and try the next one, because then we basically, the source doesn't know is this packet from me.
But why is it important to solve it then? It almost sounds like you are artificially removing one piece of data, but I guess it's not like that.
I mean, ideally, we want perfect resilience.
Yeah.
Okay, it's still a very natural notion of resilience with these k-disjoint paths, basically. So it's a weaker form where algorithmically it's very interesting, but it's I agree with you, it's not exactly the final goal we want to achieve. But we know perfect resilience we cannot achieve in general. So there's been a POTSI paper many years ago by Feigenbaum that introduced also with this problem and showed it's not possible in general. But even there we don't know when is it possible, when is it not possible, we don't know in detail. Okay, good, so maybe just one more remark, how most of these problems are solved is that you decompose your network into spanning arborescences. So what is that? So basically it's directed and routed spanning trees. So if you have a k-connected network, I think this network is 4 connected, then you can decompose it into 4 arborescences. This one, it's like a spanning arborescence, so it goes from all the nodes, and the root of the arborescence is the destination. And then you can make a second one, a third one, and you can verify that all of these are basically spanning arborescences. And then what they do, these algorithms often do, is that just go one by one through these arborescences. So first, let's say these links are down after you install these arborescences. Note that the arborescences, they need the import, because when a packet arrives, I know, okay, now this packet is coming from this arborescence, I will forward it on the same arborescence. So these arborescences are disjoint, so on every link I only have in one direction an edge. So then I will just go along the first arborescence until I cannot go anymore. I see I get stuck already there. Then I will go to the next arborescence, and then I got stuck there. And in this case, in the third arborescence, I can go up here. And you can see that this strategy, arborescence routing strategy, you can at least have, if it's k-connected, you can tolerate k divided by 2 plus minus 1 link failures. So, but we don't know anything more. We don't know whether you can have k divided by 2 plus 1 or 2 or 3, or whether it can really work for k minus 1. Okay, so now there is different problems here. First of all is like a verification problem, which can also be seen as a complexity problem. You have your network configuration and you need to decide, does it fulfill resilience? Does it fulfill ideal resilience? What's the complexity of finding this out? It seems hard, right? Because you may have to go through all subsets of link failures that are there, and this already is exponential. So can this be done more efficient? And then synthesizing the algorithms. And then there are some, in reality, some specific protocols, and one of them I want to show you is MPLS. Like telecoms in Germany and everywhere, they have a lot of MPLS protocols. And there you can change the header a little bit, and you can basically model it in a different way. So just a very basic problem. If you want to do synthesis for this problem, there are different ways. You can do games, but basically what we think is nice and what works well, at least for the basic problem, is working with binary decision diagrams. So basically we generate all possible solutions that are feasible for this instance. And then we say, okay, you can get this resilience. These are all possible ways you can get this amount of resilience in the network. And then you could still, on top of it, you could optimize for additional criteria. So BDDs give you a compact representation of all the failover routings for this instance that provide this resilience. And we are only interested in reachability, like that we can really get it back to destination. But once you have those, you could also, on top of it, like optimize congestion and things like that. or have other properties that operate. So I will not present the construction in detail, but basically I show a little example here where you have this simple 2-router network, and then you have like 3 parallel links, and then you can basically generate the, in this case, 2 resilient routings, because we have these 3 parallel links that are possible from this state. But yes, so this works. It's actually for reasonably sized networks, it's already quite good. But probably you can, other approaches may be faster, maybe even like an ILP or so may be interesting. But nice here is the BDD, it just provides you all these possible solutions. So I want to show you one network a bit in more detail for the verification. And this is the MPLS network, that is the protocol that is highly widely deployed today. And this works as follows, that you have this traffic going through the network, and the flows may go different paths. And the way it works, that now we have a label on the packet that defines the path where it's going, and you can change that label. So the protocol I presented you so far is like the header is fixed and you cannot change it, that all the complexity comes from there. But in this network, you have a stack of labels, and you can define routings based on this stack of labels. So for example, here, the first flow may come in, and then when the packets come into this network, you push a label on the stack. And here, and then on every hop, you do a swap. But you don't have to do this, but here usually you change the label in every hop so that you can see where the packet got dropped, so you keep track basically of the trace of the packet. But here you can see that we have the first flow is coming in, it's pushing 10, then it's going to 11, 12, and then it goes out there. And another flow, that the blue one that you saw, it pushes label 20, then it swaps to 21, and then goes to 22 and goes out there. And then when the packet leaves, it's popping the label. So now, how this works is like if you have a link failure, then basically you push another label on the stack, and this label is supposed to route you around the failed link. So now this link is down, so you push 30, and then on the node 6, the router 6, you already have another rule that says now swap it to 31, but it's still a stack. So underneath is still 11, and underneath is still 21. So both flows will be rerouted the same way around that failed link. And then it goes back to V3, and there you can go normal again. So this is basically this stack principle, you can go around it. So at the failed link, you push this, and then you do the normal swapping, and then it brings you to the destination. And it's nice because you can do this recursively. So now if basically you fail at V2, the link to V3 is down, you push, as we said before, the 30, but now the link to the router 6 is also down, so you basically do the same thing, you push another label on it. So that's why now from V2 we even have like a stack of 3 elements, 40 to go around this failed link from 2 to 6, and then 30 that later will bring you around the failed link from V2 to V3. So you go first to V6, and then there is a pop operation, so you already routed around the failed link from 2 to 6, and then you go on like with the rules we had before, and you pop it and you go to the exit there. And the nice thing here, there is an observation you can make, because this is like a stack kind of way of forwarding the packets or having the router labels, that you can apply basically regular automata or finite state machine theorem, or regular languages from this logician that you probably, some of you know from Büchi, that show that you can verify. So this is kind of a push-down automaton related, but then the reachability, to check the reachability in this construction, you can actually do this in polynomial time, because this is like kind of a regular operation. So you can really model the whole network as this like prefix rewriting system, and then you can determine reachability relatively fast. So you can verify actually not just whether the packet arrives there, but also whether it fulfills certain properties, like maybe it arrives there, but it also visits certain points on the way that is important to you to visit, or it avoids certain places where it shouldn't go while it's rerouted. So if you model this with this abstraction, we built the first tool. Basically, there's an OpenStreetMap. We have some topologies from real networks, like in Poland or in Europe, in Germany, and you can basically query it and say, okay, is it possible that my traffic from Denmark to Sweden goes via Iceland? So we actually, our office neighbor was the network operator from Nordernet, and he gave us this requirement, because if you go through Iceland, it will be very costly. So they really wanted to avoid traffic if there is a failure to go through Iceland. So you can verify this relatively fast. If you're interested, all the topologies and so on are also available here. So you can also play around and see whether you have a faster algorithm or a better way to do it. But this is basically what can be achieved with this push-down approach. And now, again, this is not just for reachability, but you can ask additional things like, okay, is the traffic never going in loops? In communication networks, an important property is that certain waypoints are visited. So you can ask, is it sure that my packet will go through the firewall or the intrusion detection system before it enters a certain part? Even if there are link failures, you don't want it to bypass that part. So you can have more complex queries. So basically everything you can express with a regular expression, you can verify also with this approach. And now this, basically once you have this set up, so this is just a verifier. The BDD is a synthesis solution. So now you can basically get all these tables here that the provider gives us, and again you can have a look on our website if you want to play around with it. And then you can, in this case, we compile it to this prefix rewriting system, and then we can do some formal analysis there. And then basically you can give feedback to the operator that is your configuration policy compliant even under failures. But now it will be much nicer if it will not just say, yeah, you're compliant or not, but it will say, yeah, you're not compliant, but please, in this router, change the rule, then you will be compliant again. You just a single change. Maybe the admin accidentally logged into the router and changed something. You can just get feedback to fix it. So one vision here, and that's like the self-driving network vision, is that basically you get these routing tables, you make this formal verifier of it, but then maybe you can use something like a combination of something with AI that you also help you synthesize. Because verification now with our tool, it's very fast, but synthesis is much harder to generate correct rules, or even fixing. Even finding these two places where you need to change the network is much more complex. So we are experimenting, but this is very preliminary now to see, okay, can we like automatically synthesize good configurations and then maybe train the model together with the verifier. Because then the model, the synthesizer can become much better because the verifier always gives him feedback. No, you didn't do a good job. This rule change that you proposed is not working, it's not working, and then it can learn how to configure it properly. Because the verifier will always be correct, but then the synthesizer is not necessarily correct. Okay, so this is a way, given the verifier, we may still be able to also get synthesis in a relatively efficient manner. Okay, that's actually all I wanted to say today.
Questions? So if you do this loop of synthesizing and then correcting based on the feedback of the verifier, do you have a bound on the number of iterations that you need?
No, we only have very preliminary results there. It works sometimes, but sometimes it's also not working at all. So I think it looks like very attractive at first look. I'm really not so sure how well it will work, to be honest. Maybe we are still using the wrong neural networks or so, but the hope is that it goes fast, but this is up in the sky now.
So what neural network or what?
So we actually tried graph neural networks, We also discussed with some experts in the neural networks, and they were already telling us certain problems are very hard to do with neural networks. Even like computing a shortest path or so is not working very well. So if you have a suggestion what could work there, the formal methods part we understand fairly well, but the AI approach we need to use, we tried a little bit with genetic algorithms also. That worked very well in other related problems, like in the first one I presented. There the genetic algorithm actually works quite nicely. We had to really think about how to set the genetic algorithm up so that it's really working, which is like, I didn't know that like you really need to contribute something to work well with the genetic algorithms. But for this, with this push down, it didn't work so far.
Can you say a bit more on the verification? So you said that one can use a push-down automaton to represent the stacks of different roots, I guess.
Right. It's actually a prefix rewriting system, kind of. It's not directly. You can model it as a finite state machine. Okay. That's why it's actually the complexity is polynomial.
Okay. So you don't. So
it's because it's just reachability, but yeah.
Because the property you want to check is, I mean, you had this, sorry, I forgot the term, compliance or...
policy compliance, yeah.
But does it say something about the stack content? Or?
Yes, also you basically, you need to look into the stack content because then really defines where you're going through the network. Okay. And you want to make sure certain places you're really going through and other ones you don't go through. Okay. It's kind of a regular expression you can express the path that is allowed or not allowed.
About the first part, maybe, is there a structural reason you used BDDs that made it work well? Or?
I mean, I think this was a co-author that suggested it and said this works very well, but actually I see in our field, like in networking, quite a lot of people work with BDDs. And it seems to perform very fast compared to, I think it will be faster than something like ILP. And then you also have this nice advantage that we can, on top of it, we get all the solutions compactly represented. Right. And then we can have a secondary function on top of it to select even better paths or so.
There's a very large community, of course, working on constraint satisfaction, which seems a little bit similar to what you're doing. And they certainly... I mean, they do use BDDs, they also use SAT solvers and all sorts of other tools. Yeah.
So they are internal using BDDs for the constrained programming.
I think some people do, yeah. 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 But as I say, also SAT and SFD solvers, depending on the nature of the constraints, and it's hard to know looking at this which.
But this is like a more general approach, right? Yeah. This constraint, so it's like maybe an extra complexity.
Yeah, that's right. Yeah.
But you are more powerful in the things you express there, I guess. Mm-hmm.
But I would think the main advantage that you get from a BDD is that it's canonical, right? I mean, once you fix the variable order, and I don't see why this is important for your problem.
I mean, we are really doing it because of all the solutions. I'm not sure we don't benefit from this.
That's for example, if you have a fixed point calculation to do, then that's an important advantage that you get.
I mean, the other advantage is we can use existing software tools quite well with this approach, right? I'm not too constrained programming. We also have, of course, satisfaction solving is.
Yeah. I mean, of course, my main exposure to BDDs was a predecessor to SAT solvers in model checking, and interesting to see how it's evolved from one to the other. And of course, the variable order was, in both of these technologies is vastly important.
I think it's a very old technique, right? It seems to be coming back at least in the networking side.
Yes. When I think of BDDs, I always think of the late Ed Clark. So.
Really?
Yeah, he was a big promoter of BDDs and model checking.
Okay. Nice.
Okay. Well, let's thank the speaker again.